Hello, everybody. I'm Bobby Salves.
And I'm Michael Monaco, and we're the Hazmat Guys. This is Ask the Hazmat Guys, answering your questions.
So let's take a look in the old mailbag and see what we got here. We have a question on meter correction factors.
Radiation and counts per minute.
Another question is on using firefighter bunker gear as a viable PPE selection.
The mole, a basic yet mysterious unit of measurement used in chemistry.
All right, for question number one, we have it from an unknown, I can't figure out who it was, said that just started listening to your show. Do you have any info on how to truly read a multi-gas monitor and to do correction factors? A lot of guys in my department just go until it beeps, but I don't really know what that means, just looking to help them. Well, thank you for the question. Here it is. We've heard this many times. Each meter has a specific chart that they publish with the correction factors. Typically, the action levels, which in our case is beeping, are going to be correlated with the worst case scenario. So even when the correction is the highest, it will beep in time. So now in an LEL sensor, we don't know whether it's detecting pentane or methane or propane. It only recognizes that one or more of the combustible gases are in the atmosphere, in fact. So once it's calibrated with a particular gas, the instrument will display the LEL values, assuming that all gases in the environment are that one specific gas. And if there's more, it actually takes like kind of the average. So if a sensor is calibrated to methane and it detects ethane, the instrument will display the LEL, assuming it was methane. So this training leads to a typical alarm level of between 10% LEL and 20% LEL, because most of the calibration correlations factors are really relatively close to reading this on a display. They're usually like 2 or a little bit more times or less. The logic is the combustible gases in the atmosphere will not exceed 40% of the LEL, which is 20% of the LEL multiplied by a correction factor of 2, right? So that's 40, assuming a worst case scenario. So even assuming a 25% error in the reading, the user is still well below the lower explosive limit and has time to retreat to a safe location. So if you want any more, check the manufacturer website for information or send us the make and model, and we may actually have that in stock. So cheers.
Okay, this question comes from Chris, who's from St. Paul, Minnesota. And he writes to us and he says, "Hey guys, sorry to ask the question. And I went back and I listened to the podcast again. Obviously not well enough. But you guys had a great analogy when it came to radiation, and it was understanding the differences between counts per minute and dose. You used a bullet and a gun analogy. I'm sure it was probably in a radiation episode, but I can't seem to find it. My crew and I are going over pH paper, K paper, and RAD on Sunday, and I just wanted to explain that correctly. Thank you for your time, and keep rolling those podcasts." Sure. Let's see if I can clear that up for you and not confuse you more than you already are. All right, to be very honest with you, I don't really know where half of this stuff is, but CPM, all right, is also known as counts per minute. We use this in radiation. It's the equivalent of being at the shooting range and hearing a gun go off. When you hear the gun go off, you know that a bullet was just fired, just like when an isotope fires off as energy. So the technical term for this is going to be a disintegration. Now think about it like this. If we were down at the range and we were hearing one shot every 60 seconds, then we would say this is 1 count per minute. In the isotope world, we do exactly the same thing. But instead of hearing the shot, the meter is actually picking it up. Now, the problem with just counting the shots at the range is that we have no idea how big the actual caliber of the gun is. We don't know how much damage one of those shots could do to us. All right, one of those shots could be a 22, it could be a 30-06, or it could be a 223. We just don't know. So they came up with the unit REM, which is REM, and it's a way of measuring the damage or the size of the bullet that is fired. All right? I hope all is well. Reach out if that doesn't make any sense.
Okay, question number 2. This is from Bob Dobbins from Scranton, Pennsylvania. And he asks, can we use bunker gear for all hazmat responses, and why not? I guess he's assuming I would say no. But another great question is, and one that we as a group don't have a fundamental grasp on as a whole. Hazmat is a unique emergency, one that takes a lot of research to do properly, and the selection of the PPE is one of the most. It always causes fear of maybe picking the wrong selection. So how do we do this? Well, let's start with our firefighting bunker gear. This is something that the majority of us listening to the show are very comfortable using. We have regular interactions with the dressing and the use of SCBA that accompanies it. So in reality, this is a good thing for our operators. Where the controversy really comes from is that bunker gear is not a chemical protective clothing. And this is true. It is deemed at a Class D chemical protective ensemble. I love saying that. But I will argue that this thick clothing will give you a delayed response to the chemicals that we are encountering, depending on your mission. So remember that we're using our meters and our smarts, what's between our ears, to help us. So if we're fully bunkered up and the meters are giving us an indication to perform an action or our mission, or we can't do that action or mission, then we stop. We fall back, reevaluate our PPE selection, and continue our operation. If the meters are not going into alarm, then what's the harm? Again, if there's something wrong, then we stop and reevaluate. One thing that the bunker gear is particularly good for is radiation. And this is mostly because it's thicker and it will afford us more protection, even the best chemical protective clothing out there, due to the density of the fibers. So I wish we can get into this really more in this little segment, but this is all the time we have. So perhaps in the near future, we can explore this on a full episode of the Hazmat Guys podcast. Thanks a lot.
The next question comes from KC in Philadelphia. I don't know whether KC is a male or a female, so we'll just say female. Why not? And she asks, what is a mole? Why is it used in acids and bases? And how does it affect my response? Fair enough. Okay, good question. And one that is fairly straightforward and complicated all at the same time. The first thing you need to know and understand is really what is a mole. Now, there's going to be some big numbers here, but really, come on, don't focus on them. It's the concepts I want you to know. Short answer, the mole is a system of proportional measurements. 1 mole is equal to 6.02214 times 10 to the 23 molecules. Again, a big number, but please, 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 don't get hung up on that. All right, let's use water as an example. Water contains 2 molecules, or 3 molecules, 2 types of molecules, 2 hydrogen and 1 oxygen. So if I wanted to make water, I need to go to my closet and I need to break out 2 hydrogen molecules and 1 oxygen molecule and then put them together. The problem is this isn't a goddamn car, and I can't just go grab molecules off the shelves. All right, the parts don't come like that. So then I have to sit and I got to figure out a different way of getting the molecules. So if I sat and thought about this long enough, I would realize that if I can't grab it, then I need to figure out a way to weigh it out. And I need to do this proportionally. So I may turn around and grab 2 grams of hydrogen and 1 gram of oxygen. You would think that would work, right? 2-to-1 ratio. But it doesn't, and here's why. Hydrogen is about 16 times lighter than oxygen. So the hell what, you may ask? Well, let's take a step back and think about this. Let's focus on a tangible item. Let's say beer. Let's say I'm brewing beer at home and I'm at the bottling phase. I need 1 bottle per cap to lock my goodness up. This is where I have a ratio, 1-to-1 ratio. I have a lot of beer, so I'm going to need a lot of bottles and caps, and I'm way too lazy to count all this out. So I go to the beer store and buy 10 pounds of bottles and 10 pounds of caps. That's a 1-to-1 ratio, right? Anyone out there who's held a beer will tell you you're going to get a shitload more caps in 10 pounds than you're going to bottles. So it would be smart to know how much a cap weighs over the bottle. This is exactly what they did with molecules. Through some wizardry magic, someone determined that if you take a molecule and you take the molecular weight of that molecule or that element and you turn it into grams, then you have 1 mole. It doesn't matter what the weight of it is, nor the size of the molecule. If I have 16 grams of oxygen, then I have 1 mole of oxygen. If I have 18.1 grams of water, then I have 1 mole of water. And since the mole is equivalent to 6.22 times 10 to the 23 molecules, or as I like to say, a shitload, then I can now proportionally weigh out the chemicals we're going to use in a chemical reaction based on moles instead of grams. Whew, well, that was a lot. All right, so why the hell is this used so much in acids and bases? Well, acids and bases are used extensively to create a chemical reaction. Whether we're donating a proton or accepting a proton, the lab rats want to make sure that for every reaction, they have an acid or a base molecule. No more, no less. So we're going to see the concentrations of these acids and bases listed 2 different ways. The first is going to be molality. All right, and all this is the number of moles of solute per kilogram of solvent. The other term you're going to come across is molarity. This is the number of moles of solvent per liter of molecule. So a 4 molar solution is going to be stronger than a 1 molar solution. How does this change our response? Well, it really doesn't, other than the fact that a stronger molarity substance is going to take more acid or base in order to titrate it down. But since we don't know the numbers to begin with, we're going to be focusing on changes in our pH paper. So in reality, a higher molar or a lower molar solution of an acid and base is only going to change how much stuff we need to titrate.
Well, that wraps up another episode of Ask the Hazmat Guys.
You can find us on Facebook, Twitter, and Instagram, or our YouTube channel at the Hazmat Guys.
If you'd like to send us a question for us to answer, call our comment hotline at 843-628-1484 or send us an email at feedback@thehazmatguys.com.
And remember, don't just get on the job, get into the job.